Hello and welcome back to the video lecture series on chemistry of alkenes and alkynes. This time we are going to discuss how you can make new alkynes starting from a terminal alkyne. Terminal alkyne has a typical hydrogen that is associated with it, which is an unusually acidic hydrogen for a hydrocarbon because the conjugate base can accommodate the electron pair into a sp hybridized orbital. This pK value is unusually less, and with a suitable base such as sodium amide, you can get a sodium salt of the terminal alkyne, which is pretty nucleophilic. It is a basic species as well as a nucleophilic species, and therefore, if you treat this with a proper electrophile, which is supposed to undergo SN2 reaction, you are going to get this type of reaction, which will establish a new carbon-carbon bond so that you get a new alkyne. And for the reaction to happen, you need to have R1X, which is susceptible to SN2. If you don't have that, then your reaction will be, if you treat this thing with a tertiary halide, then obviously bimolecular elimination will take place and you will get nothing of this kind. An example is the synthesis of 2-pentyne from 1-propyne. So you have a molecule like that. You can think that I am trying to synthesize it by putting a negative charge here and a positive charge here. So those two are your synthons. So you have MECH2 plus and MECC minus. Synthons are idealized charged fragments which show the polarity of the reagents, but they are not necessarily the intermediates involved in the reaction, because the anion that you derive, the sodium salt that you derive from the propyne, will be a strong base. You don't expect this reaction, strong base as well as a strong nucleophile. You don't expect methyl bromide or ethyl bromide to undergo ionization in this reaction medium to give you the ethyl cation. First of all, ethyl cation is not very stable and it's difficult to form. Secondly, in presence of such a strong nucleophile, this carbon being already electrophilic, it will cleanly undergo the SN2 reaction, and there is no scope or no way that a SN1 reaction can happen. This is far too nucleophilic to allow this molecule to survive long enough to undergo heterolytic cleavage so that a carbocation may generate. But when you think in terms of how can I synthesize this molecule by disconnecting or deconstructing this carbon-carbon bond by targeting this site of this molecule, you are going to end up with a negative charge here and a positive charge here. Because if you do the opposite thing, if you do the negative here and the positive here, then that makes absolutely zero sense. Because on a sp hybridized carbon, why should you put a positive charge? It likes negative charge, man. So put a negative charge there. You don't have to put a positive charge here and make life difficult for you, because finding out that reagent which corresponds to an alkyne carbon which is actually electrophilic in nature is going to really tough. So you don't do that. So you have a minus charge here which will come from a terminal alkyne. This terminal alkyne can in turn be coming from an acetylene by disconnecting this particular bond. So you can have downstream, you can have a second SN2 reaction happening in terms of the retrosynthetic analysis. So in terms of the forward synthesis, you start with acetylene, deprotonate one of the hydrogen, react it with Rx so that you can get a terminal alkyne, Rx obviously being amenable to SN2, and then go on from there, deprotonate again, react it with the second electrophile R1X, eventually end up with this thing. So this is the retrosynthetic analysis, which is the problem solving technique of transforming, mentally deconstructing the structure of a synthetic target molecule. This is the target molecule that they have given you, and you simplify it till you get easily accessible structures like acetylene, Rx, and R1X. So this unit is coming from acetylene, that unit is coming from Rx, that unit is coming from R1X. So the operation, the mental deconstruction of the whole molecule into such smaller fragments by several different techniques, by targeting specific bonds, that is the retrosynthesis. That's the mental operation. In real life, you have to do the reverse. So mentally, you are disconnecting the CR1 bond first. So when you are doing the reaction on the reverse order, it is the last bond that you are going to form, and it is the RC bond that you are disconnecting second, but it is the first bond that you are going to form in the synthetic operation. So retrosynthesis is just the opposite of the synthesis. Synthesis is actually something which you do on the bench top, but retrosynthesis is something which you draw in your notebook, which you draw or do in your notebook, and you come up with a plausible suggestion, a proposed retrosynthetic scheme. It may or may not work, but to do that, to draw a plausible scheme, you need to understand the basic chemistry. Just like you can't put a positive charge on this synthon or a negative charge on this synthon, it is better to put a negative charge here and this positive charge here. These idealized charge fragments are synthons, which may or may not be the intermediate, as I have told you, in the reaction medium. In this case, obviously, this is a synthon which is actually the reactive intermediate. You get to access this by deprotonating the acetylene. You have to deprotonate acetylene, otherwise acetylene cannot act as a nucleophile. This one is coming from the terminal alkyne. That's also idealized fragment synthon, which is an intermediate. But as I have told you, R1 plus or R plus, they are not going to be generated from R1X or Rx respectively, because these are SM2 reactive electrophiles. In presence of such a strong nucleophile, they have absolutely zero chance of undergoing a heterolytic cleavage. Okay, now you have the other thing, that is the transformation of the interconversion of the terminal and non-terminal alkyne. Just like the more substituted alkenes are more stable compared to less substituted alkenes, more substituted alkynes are also more stable. So here we have two isomeric alkynes. One is the 1-pentyne, the other is the pent-2-ine. And as you can see, heat of hydrogenation value is less for pent-2-ine compared to pent-1-ine, which means that the pent-2-ine isomer is more stable because of the hyperconjugation and inductive effect of the alkyl groups. Here you have ethyl and you have methyl. Here are 2 hydrogens, here are 3 hydrogens, so number of hyperconjugative hydrogens are 5. Here you have only a propyl group with 2 hydrogens, 2 hyperconjugative hydrogens, so this one is expected to be less stable. So if I can somehow, if we can somehow subject this molecule to an equilibrium, where on one side we have a terminal alkyne and the other side we have an internal alkyne, then this equilibrium is supposed to be favoring this, internal alkyne, because internal alkyne is thermodynamically more stable, and that is exactly what is done by subjecting terminal alkyne, treating this with sodium hydroxide and ethanol, and heating the reaction mixture at 170 degrees centigrade. Because these reactions are, kinetically not favorable, you have to increase the temperature very much. Now, how is that happening? So you are basically exposing the alkyne with a base. So you can use sodium hydroxide in ethanol, then that means that reaction can have hydroxide or ethoxide, both can be present in the reaction medium as a base, and their pK values of their conjugate acid water and ethanol, they are pretty close, and therefore you can use any one of them to show what is going on. So the first thing that can happen is the abstraction of the proton, terminal hydrogen, that is the most acidic proton that is being present here, and ethoxide can take away this proton, so that we get ethanol as well as the terminal alkyne, the sodium salt of the terminal alkyne. But the big question is that this pK is 25, that pK is 16, so that's a strong acid, that's a weak acid. So equilibrium should be favoring that side. So the number one equilibrium is favoring that side. As much as we would like to deprotonate this hydrogen all the time, but there are also other hydrogens that can be deprotonated from this molecule, and the conjugate base developed here can also get some resonance stability. But because it is it is not a terminal proton of the alkyne, the pK value is only 38. This is like 10 to the power 13 times more acidic, so most of the times this will be deprotonated. But as we are using ethoxide, this alkyne is never completely deprotonated. It is deprotonated to some extent in this way, or to a lesser extent in that way. So this hydrogen can also be abstracted. If that happens, then let us look into the equilibrium direction. So this number 2 equilibrium, that's also kind of favoring the alkyne itself, because we are getting from a weak acid, we are getting a strong acid. Let us draw the resonance structure. If we draw the resonance structure, then this is basically an allyne type thing, where you have a negative charge on this terminal carbon. That's a base, and you have ethanol in your reaction medium, which is a proton source. So you can protonate it. Let's see how this equilibrium behaves. ethanol has a pK of 16, and this hydrogen that you are going to incorporate here, that pK is also about 38. That pK is also about 38 because that's a alkyne hydrogen. This hydrogen and that hydrogen will not have exactly the same pK, but let's assume that they're pretty very close. So if it has a pK of 38 and this has a pK of 16, then where should the equilibrium lie? Obviously in the forward direction. So number 2 equilibrium is favoring this one, but number 3 is favoring that one. Okay, that's interesting. But this hydrogen can again be abstracted from ethoxide by ethoxide to give you that one, which is again an equilibrium which would be favoring the alkyne and not the conjugate base, because here you have pK 38, here you have pK 16, so it's favoring that one. But that's also another there is another equilibrium here. There is another resonance structure you can draw here, which places the negative charge by delocalizing it through this pi network onto the terminal carbon. And once you have that on the terminal carbon, you have ethanol present in the medium, and now this carbon can take away this hydrogen from ethanol to give you this one. So we know that a carbon hydrogen bond right adjacent to a sp carbon of an alkyne moiety that has a pK of 38, so this pK is also 38. And if that pK is 38 and that pK is 16, this equilibrium will be favoring the internal alkyne. So you see, from this to this, you have 4 equilibriums, 2, 3, 4 and 5. 2 of them are favoring this one, but 2 of them are favoring that one. So if that happens, we are forced to say that there is an equilibrium between octoanion and octoine, and thermodynamics tells you that because octoanion is less stable compared to octoine, the equilibrium will be eventually favoring and accumulating the octoine. So that way, using a base which never actually deprotonates either the terminal alkyne or the internal alkyne, any of the hydrogens. This ethoxide or hydroxide does not deprotonate any of these hydrogens completely, any of these alkynes completely, because if it does so, then things will become even more interesting. So this way you can establish an equilibrium between the terminal and the internal alkyne, where the internal alkyne is dominating. But let's take inspiration from this particular fact. Can I go in the in the opposite direction? If this equilibrium is favoring this octoine, then can I go in opposite direction? Sure. Use a base which can completely deprotonate this hydrogen, this alkyne, and this hydrogen can be completely taken away quantitatively. So if there is an equilibrium between those two and you are using a particular base which has the capacity of deprotonating this terminal alkyne completely from this hydrogen but not these hydrogens, so it's strong enough to completely deprotonate that portion of the molecule but not completely deprotonate these things, then you have a situation where in this equilibrium the internal alkyne, the terminal alkyne, it's getting consumed and driven, away from the equilibrium. To keep the equilibrium constant, more and more of this internal alkyne will convert, more and more terminal alkyne will be produced, more and more terminal alkyne will be deprotonated, which will induce more and more internal alkyne to convert again, till the whole internal alkyne is converted into the terminal alkyne or its salt, and then you do a acid workup, aqueous acid workup, so that you end up with the terminal alkyne. So that's basically exploiting the most acidic proton, because this is the most acidic proton of all the possible deprotonation sites in both the terminal as well as the internal alkyne. You are manipulating this acidity, and following Le Chatelier's principle, you are drawing this internal terminal alkyne away from this equilibrium so that the internal alkyne gets converted into the terminal alkyne as you are forming the salt. So that's a contra-thermodynamic isomerization or conversion. You're basically getting a a less stable alkene or alkyne from a more stable alkyne. So how can we do that? But this time you are using a much stronger base amide. That pK value is 35. That pK value is 38. So this equilibrium will be favoring this one. I am taking away this proton. Recall this is an internal alkyne, so there is no hydrogen with a pK value 25. All of these this is 38, that is 38. So this might as well be taken up, but that's not necessary for us to consider right now. This hydrogen will be abstracted and I will get a conjugate base. And that conjugate base is resonance stabilized, gives you a alkyne, gives you a alene derivative with a negative charge, which has a conjugate acid whose pK is 38 and this pK is 35. So this second equilibrium is favoring this direction, and then you take up the one of the other terminal hydrogens. So you have taken one hydrogen here, and then from the same carbon you are taking away the second hydrogen. So there must be present at least two hydrogens on this side. So you are taking away the second hydrogen, you will get another alene derivative. The same thing, equilibrium will be favoring this one because this is 35, because this is 38. So equilibrium favors the alene intermediate. But once you have the conjugate base, the ammonia acts as a proton source, and you can draw the resonance structure here. So the negative charge goes here, and this can take away the proton from here. So this is pK is 38, and now you have your internal alkyne. So up to this point, this one is favored, because up to this point, 1, 2, 3, up to this point, there is basically equilibrium between these two. The up to this point, I should say up to this point, not up to that point. Up to this point, 1, 2, 3, 4, there is equilibrium between the internal and the terminal alkyne. And we know that terminal alkyne is less stable, internal is more stable. So this one should be like more favorable. But now see the pK differences. It's like pK difference 3 here, pK difference 3 here, pK difference 3 here, pK difference 3 here. But now you have a hydrogen which is considerably more acidic than any other hydrogen present in the reaction medium. So that pK is 25. NH2 minus is there, whose pK of conjugate acid is 35. So this will draw the overall equilibrium. The fifth equilibrium will disturb the equilibrium 1, 2, 3, 4 by taking away and completely deprotonating this molecule, and this will be forming as a sodium salt, and this will continue converting itself into this one, which will helplessly go over into this one. More and more will be converting into this one, which will again be deprotonated into this one, so that eventually you have the sodium salt. And after that, once your reaction is over, you work up with water, so you get the protonation here. So it's a contra-thermodynamic isomerization. You are exploiting the unusual acidity of the terminal hydrogen. So you can actually go for that. So the overall transformation is sodium amide. Transform Kulle, you need to have two hydrogens here. Just I have told you need to have one hydrogen for the first step, second hydrogen for the third step, etc., etc. If you don't have enough hydrogens on the carbon adjacent to the carbon-carbon triple bond, then no sort of isomerization can take place. So equilibrate the non-terminal alkyne with a very strong base such as amide base, and these things are done in even at room temperature, so that the terminal alkyne anion is formed, which are rapidly quenched by the proton source such as water or acid water. And when you add water, it has the RNH minus that is present in the reaction medium. It will deprotonate, or the terminal alkyne will deprotonate this water, so hydroxide will be produced. But in presence of hydroxide, this will not isomerize to this one, because that will need 170 degrees centigrade, and which you are not going to give. You are doing the reaction at room temperature. So one of the beautiful reagents that you can use for this purpose is the organic superbase, which is the potassium 3 aminopropylamide, KAPA. You use it a little bit of excess in 1,3-diaminopropane solvent. the temperature is 15 to 20 degrees centigrade, so there is absolutely zero chance of isomerization of the internal alkyne, the terminal alkyne into the internal alkyne when you are working up with water or something like that. And this reaction is known as the alkyne zipper reaction. Just as you draw the zipper of your bag to close down the pouch or sachet or something like that, you are basically zipping this carbon-carbon triple bond from that side to that side, or maybe from that side to that side, because in both directions this carbon-carbon triple bond can actually migrate. If you are interested, you are encouraged to draw out the mechanism involved in shifting this internal alkyne onto the very end of the chain. So it can go here or it can go here, because you have couple of hydrogens here. All the time you have couple of hydrogens here, so there is no problem. Also you have couple of hydrogens in all these positions, so you can draw the zipper on both directions. And the extremely fast reaction, because the reaction time is only 1 to 2 minutes. It's a concerted protonation deprotonation thing that KAPA can do. You are just doing the deprotonation and then you are doing the protonation. If something can do this reaction in a single step, just like KAPA can, this NH minus is taking away this pK38 proton, and this carbon-carbon triple bond is actually taking up this proton from the NH2. So in the single step, you are basically doing a couple of things. You are doing the deprotonation as well as you are doing the protonation. So in this way, KAPA can function very efficiently, so that eventually this molecule will be totally isomerized into that one, and on water workup you will get the terminal alkyne. The only point that remains to be discussed is that for something like this, for alkynes, you need to have couple of hydrogens here, so that this chain, the zipper can move in this direction, or at least couple of hydrogens here, so that this one can move in this direction. Because you have, isomerization will not take place here, because you have methynes here. The number of hydrogens are less, only one hydrogen is present. As a result, you don't have this type of isomerization where you will need presence of at least 2 hydrogens to shift the carbon-carbon double bond in that direction. You don't have 2 hydrogens, you only have 1 hydrogen. Isomerization will not take place. So if you spot a methyne carbon, so if this thing was like that, এই জায়গাটাতে কোনো মিথাইল ছিল না, তাহলে যদি কাপা দাও তাহলে এই কিন্তু মাইগ্রেট করে এদিকে চলে যাবে। এদিকে যাবে না, নো ওয়ে, কারণ এদিকে নাম্বার অফ হাইড্রোজেনস কম আছে। সো ইফ ইউ সি সামথিং লাইক দিস, দেন লুক কেয়ারফুলি অ্যান্ড জাজ যে এটা কত দূর যেতে পারে। কারণ এটা মাঝখানে যদি এই জায়গাতে থাকতো, তাহলে প্রবাবলি কার্বন ডাবল বন্ড শিফট করে হয়তো এই দিকটায় আসতে পারতো, কিন্তু তারপরে আর যেতে পারতো। সো আই thank you for your patience. I hope these things have been cleared up. And this concludes the study material 8 video lecture, which has now become a 3-part video lecture. And I will be seeing you in the next one.